Okay, this is some good news about Fukushima. When you look at these equations and stuff, what you realize is that this up here equation indicates that there's going to be eventually an amount of, say, decay that's equal to the amount that's growing. Now, in the case of the uranium-235, which is the primary decay method of these reactors, except for number 3, which is actually a mix of uranium and plutonium. By the time you reach right in here, okay, which is about the 100 to 120 year mark, they stop growing. That's good, because guess what? Even though nuclear radiation has 700 million year life expectancy for it to half-life, it won't get no worse than that. Then it'll start declining eventually. My equation does not predict the actual point of decline. And that's because it's such a big number. Now over here, if I continue these forward, it becomes an infinitesimally small amount added to it, and this is the iodine 131. But we know that the iodine 131 half-lives every 8 days. See, this gets down to the 750 million mark again. That's how much is going to actually come out of the reactor for 700 million years before it fully half-lives. But as you go along, eventually enough half-lifing occurs that the amount right here, this 60 by 10 to the 6, starts to go down. That's your answer to Z, or this number right here. That 60 by 6 to the, no, that's actually P, excuse me, which is based on the 3% from Wikipedia on nuclear byproducts that make up the radioactive decay of uranium-235 and uranium-233, then 6% for strontium, which is only, it's less than 10% of the total radiation being put out at any one given time from a nuclear reactor. Now, saying all that and looking at these figures here, this 60 times 10 to the 6 will slowly start to decline. The P will start to decline. And when it does, it's going to reduce this number. But you're probably talking about going out to like an equations, you're talking about maybe 2-3 million equations on iodine 131 before you would start seeing a reduction. In this one is likewise, you're talking about a long time from now. But that's really good news when you think about it, because there will be some change in this number right here, the 60 times x to the 10th, 60, 10 to the 6th, and then that's going to change that 480 to a lower number, and you're going to have less radiation to deal with. I just ramped it up. I just did the equations up to where it would level off. I mean, if you want to keep going and see if you can find it going down, you can. But remember, I went from an initial amount based on radioactive percentages and how much energy was being put out. In this case, this one right here, which came from Japanese Times, article listed on Lisa Haven's site, "We're being nuked, what they're not telling you about Fukushima, etc. disaster." So that's pretty much that. I just thought I'd tell you all that because In these equations, you might not necessarily see everything I'm showing you, but these sets of equations allow you to calculate up to when it starts to get to the maximum, where you have just as much decay as you have input, but given enough period of time, your input will start going down. Because your half-life, you'll get closer and closer to your half-life. Even though I included half-life in the equation. This 0 is what's called 0.5D, is actually the half-life after, in this case, first 8 days, and then 16 days, and 24 days, so forth. And this one over here, the 0.5, it was times 0 initially for the initial calculation. Then after that, it's 0.5 times D, and this D would be the first one 643 by 10 to the 9th. Then the next time you go through the equation, it would be 465 times 10 to the 9th. And if you follow the equations, they get smaller and smaller increases. Eventually, that would start to decline. And that's some good news, particularly when it comes to the iodine. Because, I mean, I'll have to figure up an equation for it, is what I'm telling you. But that iodine half-life is going to have an effect. It's already pretty much setting at max. This one is pretty much setting at max in 100 years. So that's going to be a while. This is only in becquerels, and the becquerels are on a daily basis. The person who gave me this information that came from the Japanese Times, this Lisa Haven girl, was 2 billion becquerels a day. Now, to tell you how this equation kind of works while we're sitting here, I want to explain the equation to you. Okay, you have the Y there. That's your amount, it's your initial amount of radiation, okay? That's your Y. Your P is the continuous output. Eventually, that will decline. So eventually, you're going to have a summation in there to change the P. The Z is your half-life. Now, Z, like I say over here, see if I can find it. There it is. Z equals units, Z units divided by P units. That means if P is in days, Z has to be in days. If P is in minutes, Z has to be in minutes. So if you've got a 8-day Z and you've got a 1-day P, then Z has to be changed to is 8 days. But if you had a 1-hour P, it would be 190, I think it was 192 hours for the Z. Then here you've got 0.5 times your Y plus P Z times Z minus 1 sigma over X equals 1. And that equation comes up to 1 minus X over Z. And when it comes to the 1 minus Z minus 1, that'll give you your summation length. X will keep going up each time and thus reduce the total number amount. Eventually it gets to 0. When Z equals X, when X equals Z, it becomes 0 and the calculation ends. That's as far as this equation will take you. And that's roughly where these are coming in at. They're as far as the equation can take you. After that point, you have to come up with a different equation unless you want very minor changes in your values. That was an equation there based on becquerels. As you can tell, it came out to, it was 30 years. So you times that by 365 days a year, it comes to 10,950 days. You can see how that transferred through all the way through. Let's get this other way so you can see it. See how it went up here and down here, right down here too. And these equations, or solutions I should say, this solution here substitutes here, and then you redo the equation, but you don't have to substitute all the way up here to redo the equation. You can go down here to this equation and just simply add it to this, then here divide it by 2 plus this, then minus this with that part from this part that you just added that to. Now let's see if I can get over here and show you a better example of that. You see here where it says 0? Well, that's where you would put those numbers at. Over here is where another 0, 0.5 times 0. And you can see how the equation goes there. It's the 0 or the d value of the previous calculation that you've done on it, plus 1.3 times 10 to the 12th, which is the amount that it figures out to, minus 0.5 d plus 657 times 10 to the 9th. Make sure you keep your things right here. These things right here. These little, I forgot what I think they're called. They're not called commas or anything. I can't figure out what those things are called off the top of my head. But those will be symbols. Parentheses. These parentheses here divide out the equation. So make sure you put your parentheses in the proper equation, in the proper point. Like I would actually, oh, that should be there. That's right. Yeah, that's right. That's basically the way it goes. Like I say, this equation only works up to the pretty much where it levels off, and you get that max amount. Then you have to do something with the P over here, and I'm working on that. But just to tell you that there is some good news in these numbers, in that this right here is probably going to show a significant decline by now, where this right here is still going up. And I don't know about the other types of radioisotopes that come off of it or not, just these. Well, Keith Willis here, or Thomas Willis. Have a good day.